Last lesson, we spoke about how the electric field pattern could be simulated using some software. And we have already seen that the field pattern for a pair of oppositely charged parallel plates is a uniform field in between the two plates. However, that was just a simulation on a computer. And what I want to do for you now is to try to justify from the Coulomb force why that would be the case. So what we've got here is a picture of two parallel plates. Now, I've written in the title that they're supposed to be infinite parallel plates so that we don't get any edge effects where the field curves. If we want a truly uniform field between the plates, it does need to be infinitely large plates. However, electrons are very small compared to human distance scales. And so any object that is going to be even moderately sized for a human is going to be effectively infinite for an electron that is in the middle of the two plates. So if we just concentrate on the zone and using the zone in the middle of the two plates, it doesn't really matter that there'll be edge effects because the electron will never go near the edges of the plates. Okay, so let's have a little think about this electron. Here is a plate that has been charged up with some electrons, so it's become negative. And the same number of electrons that are on this plate have been removed from this plate. It's effectively a capacitor arrangement. We can now evacuate the space in between the plates so that we can consider that this is a vacuum that's in between the two plates rather than a material dielectric. And we can ask what would happen to an electron that we dropped at the exact halfway points between the two plates. So the electron is negatively charged, so you can see that it will be repelled from this plate and it'll be attracted towards this plate. And if we put the electron in exactly the center of the two plates and the two plates contain exactly the same charge density, then you can hopefully appreciate that there will be exactly the same amount of push from the left-hand plate as there will be pull from the right-hand plate. And that's going to add up to a certain number, whatever number it is. Now, what number will that be? Well, we need to consider that there'll be a force pulling from the positive plates. But now that we're dealing with a two-dimensional, well, technically three-dimensional situation, we need to start making some mathematical shortcuts to allow us to properly do this problem, because there will be about 10 to the 20, 10 to the 21, at least, electrons on this plate, and we can't possibly add up that many Coulomb forces. There will be, for every single positive charge on this plate, E from there, divided by the distance between them, which is d by 2 squared for one that's immediately there, multiplied by the 1 over 4 pi epsilon naught. And that's just for a single proton there. We would then have to ask ourselves about the proton that's there, and there, and there, and there. And for each one of these things, we then have to modify the d ever so slightly because it's a diagonal rather than a straight line. And to do that sum 10 to the 20 times is just not doable. So what physicists often do when dealing with a vast number of particles is to not consider each particle as a separate entity, but to smear it out as a distribution of charge. So instead of asking about an individual positive charge here, what we could do is project kind of a cone from the electron, and we could just ask how many electrons are in that patch of, protons are in that patch of plate to attract the electron in. Now, you've got to remember that this plate is a two-dimensional object, so it's sticking out the board. And if we could look at it from that side, it would look like a square. And so this triangle shape that I've drawn is actually more like a cone when it lands on the square plate. And the area of the patch of metal that contains the charge will be proportional to the radius squared, because it's a circle. And this radius here will be proportional to this distance here for a particular angle here, because it's just a right-angled triangle. So once I fix what this angle is, then by trigonometry, this radius here is entirely determined by this distance and this angle. So if we just consider that the angle is an infinitesimally small angle, as we've done many times before, then we can set that angle to whatever we want it to be. And this radius will therefore just depend on the distance from the plate. And therefore, this distance here determines how much charge is in the sphere. And you can see from the r squared bit that as the distance goes down, so if we were to move the electron a little bit nearer and keep the same angle, then as the distance decreases, the area decreases. There's less charge. Okay, let's come back to that idea in a minute. Okay, so what we can do is ask how much force is there due to this area of charge? And that's a sum that can be done, but it involves you being able to integrate over 3 different dimensions at the same time. So we're going to skip the maths bit of it, unusual for us, and just appreciate that there is an amount of charge there that is doing the attracting, and we could add up that charge, and then we could use this distance, assuming that that angle is infinitesimally small. You can see in principle that that sum is something that we could do. And then if we wanted to, we could project another cone up there and do that bit of charge, and another cone over there and do that bit of charge. And so if we integrate over the angle around there, we'll get the whole plate. It's a doable calculation. And some of you that go on to do either maths or physics next year, you will do this calculation. Once you've learned a little bit more about integrating in more than one dimension, it's fairly straightforward to do. Okay. The point is not to obtain a number, but to accept that there is a number that can be calculated. And then what I could do is I could take the line from the cone and extend it backwards, and this one, extend that backwards, and I've got another cone on the other side, which the electrons in the middle will be the same size. And you can see that the calculation's gonna be symmetrical. This is attracting, this is repelling, and it's the same amount of charge, the same distances are involved. So whatever the number is that's attracting here, it'll be the same number repelling here. So I could obtain a force arrow in this direction, and it will be the same as a force arrow in that direction, and I can calculate the force on the electron. Right, let's move the electron and have a look if it's somewhere else. Let's put the electron a little bit nearer to this plate. And we're going to keep the same angle when we draw the cone. The same angle on either side. Now what you can see is that the electron is much closer to the positive plate. And so when we talk about the Coulomb attraction, which is proportional to 1 over the distance squared, well, not d, let's have r. We're now much, much closer to this plate. So r has just gone down by a certain factor, which means that the this r here, this distance, that's just gone down, which means that this plate is now attracting more because the electron is now closer to it. But at the same time that it got closer, and therefore the denominator of this equation got smaller, and therefore the overall force got bigger, at the same time that that happened, the amount of charge that is doing the attracting, that went down. Because if we've kept this angle the same, when we moved closer to the plate, this is now a much smaller circle than it was before. When we were in the middle over here and we drew the same angle in, we had lots and lots of charge. But now that we've moved closer to the plate, we've got a much smaller amount of charge that's doing the attracting. Now, the force is inversely proportional to this distance. So as the distance went down, the force went up, and there was an r squared involved there. But also when we moved closer, the amount of charge went down. And because the amount of charge is proportional to the surface area of the circle, which is also proportional to the distance squared, as the force went up by r squared, or the change in r squared, the amount of charge has gone down by r squared. And in actual fact, the two effects have cancelled out. So that the force at this point, due to this little angle theta, is exactly the same as it was when it was in the middle. The distance has gone down, but the amount of charge has gone down with it. And the two things have cancelled out because they're both proportional to r squared. Likewise, over here on the negative plate, we're much further away from the negative plate now, meaning that the inverse square force means, from the Coulomb, means that there's less repulsion from these negatives to this electron. But now there's much more negative charge doing the repelling. And again, the distance has increased, but the area has decreased. And there's an r squared in both of those things. The Coulomb force has the distance squared on the bottom, meaning the force has gone down by a factor involving r squared. But this is a circle of charge whose area goes up as r squared. So again, the factors have cancelled out. Now really, I'm just waving my hands at this point to try to get you to accept that the force will be the same all the way across this, this distance between the plates. If you're very, very, very close to the positive plate, you get a very small amount of charge doing the attracting. So even though you're very close, it's a very small force overall. And if you're very far away from the plate, even though the force has gone down because of distance, it's gone up because of the amount of charge per angle. Which means that the force here is the same as the force here, which is the same as the force here. It works for any angle. If you want to do it at a diagonal, that works too. You could do that. If you could draw, you could. Now this time, you just appreciate that there is an upwards component to this force and a downwards component to this force, but the magnitude of the forces will be the same and the forces are in opposite directions. So when you resolve horizontally, they'll both be pushing sideways. But when you resolve vertically, the forces will cancel slightly. Because whereas there's an upward component here, there's exactly the same angle over here somewhere where there's a downward component from these electrons and these protons and an upward component from these ones. That's why we need it to be infinite, because if we start taking this electron down to the bottom, there'll still be the upwards force, downwards force from all those electrons over there, but there won't be any upwards force because there are no electrons down here. So that's why we need it to be infinite plates, really. I'm not going to do the integrations and the calculations for you. I'm just trying to give you an idea that the r squared on the bottom of the equation and the r squared on the top that's hidden inside the amount of charge when the charge is spread over a circle, they cancel out. Okay, so how big is the force? Well, physicists love to play a game, which is called, it doesn't matter how you get the answer. And the integration that I just described, where we spoke about actually taking the Coulomb force as a fundamental starting point and then adding it all up, it can be done, but it's quite cumbersome to do. Can we skip to the answer straight away? And the answer is yes, we can. Because if we accept that this is a constant force, if my hand waving, even though it hasn't established for you the size of the force, if you're willing to accept that it is a constant force, then what we can ask is, well, if we actually take one of these electrons and we push it all the way to the other plate using a force F, sorry, other way around. Sorry, other way around. Take an electron from this side to put it onto the plate. We have to push it against the force F, whatever the F is, whatever force it is that is pushing that way. We're going to exert ourselves an equal and opposite force in this direction, and we're going to move an electron from the positive plate to the negative plate at constant speed. So we're not going to invest any kinetic energy. We're not going to accelerate the thing. These forces are balanced. We're just going to push the electron from one plate to another. Now, we know that from year 12 energy work, that when you push an object through a distance, you do work on the object and you invest energy in the object. So how much work do we do? Well, we do F times D, force times distance. And that is the amount of energy we invest in the electron. But it's an electron, and we know all about the energy of an electron because we've got a voltmeter that measures it. So when we attach a voltmeter between the two plates, the voltmeter measures the joules per Coulomb difference between the electrons here and the electrons here. So this electron in particular has traveled from here to here. And while it was traveling, we did work on it to give it more energy. The electrons here have more energy than the electrons here, and the amount of energy they have extra is whatever work done we just did to it. And that's given to us by V. It's the potential difference, the energy per Coulomb. So we just need to take the reading on the voltmeter, and we just need to multiply it by the charge, which I guess we're using an E, so let's write an E. So this is the work that was done, and this is the energy that it received as a result. So we can now just divide by the D, and we've got straight away the answer to the question, how big is the constant force? It's equal to the potential difference divided by the distance between the plates multiplied by the charge, whatever it is that's in the gap. And because we're looking for the electric field, we can remember that the electric field is the force per unit charge. So instead of talking about E lots of charge, we need to divide away the charge so that it's only one lot of charge. So we need to divide by the charge. Remember, F equals QE. So E equals F over Q. And in this particular case, we're using a charge of E, which means that the electric field between the plates is V over D. And notice that V is a constant number. D is a constant number. Neither one of them change. As soon as we have charged these plates up and set them a certain distance, it's fixed. Nothing changes. In particular, there is no distance as a variable. So as we move across here, whether you're here or here or here or here or here, the horizontal distance or the vertical distance, it doesn't appear in the formula. It's just constant divided by constant. So this might be 1,000 volts. This might be 10 centimeters, 0.1 of a meter. So you just divide 1,000 by 0.1 and you get an electric field strength of 10,000 newtons per coulomb. It's just a constant number. So because it's a constant number, we represent the direction by lines with an arrow, and that direction is in the direction that a positive charge would move in. So a positive charge, not an electron now, a positive charge would move from positive to negative. So we can draw in arrows like this, and those directions do not change, because we said that it was just a constant force from one side to the other, and any vertical bits cancel out because any upwards pull from the top of the plate is cancelled out from a downwards pull from the bottom of the plate. So the arrows are horizontal and they have a constant magnitude for the electric field, which translates to a constant density of lines. So when we draw these lines in, we need to draw them so that they're evenly spaced. That's not very good at the top. Please draw them with a ruler. Please make sure that if your plates are vertical, your lines are horizontal. And please make sure you put this bit in a box, that the electric field for this arrangement is a constant number, the potential difference between the plates divided by the distance between the plates. So you now have two formulae for electric field strength. You have a formula from the Coulomb law for a point charge. That's this one. This is a point charge, and this is parallel plates. So please don't muddle them up. You've got to use the right formula in the right situation. If you're asking what's the electric field strength around a lone proton all on its own, or a sphere of charge, that works as well if you're outside the sphere, then you can use this formula. But if you're talking about the electric field strength between a pair of plates, then it's this one. Okay, so I'm recording this. So I'm going to zip through, and if you need to add to your notes, you can just play the recording back a little bit later, because I noticed that we're kind of halfway through and I need to carry on to the next bit. So one advantage of lockdown, at least, is that you can watch this back. Okay. This is the electric field between the plates. Remember that bit, between the plates. Right, as promised, what I'm going to do now is make a tiny little gap in the positive plate. A tiny, tiny little hole. And what this means is now that when an electron finds itself in this gap, remember, these arrows show the direction of a force on a positive charge, and electrons a negative charge. So if an electron were to find itself in the gap, and we'll talk about how that might happen in a minute, it will experience a force that pulls it across the gap. And that force will be E times V over D. And it's going to accelerate across the gap, gaining energy the whole time. And by the time the electron reaches this plate here, it will be zipping along with a kinetic energy that's equal to the energy it just gained, which is kind of this formula backwards, and we come back to E times V. So if you multiply by D, it'll just be E times V, force times distance. So this electron is about to escape with a kinetic energy if it passes through the tiny little gap. At which point, the electron will immediately attract straight back to the positive plate, right? Wrong. You see, the same analysis that we were just doing still works. So let's have a little look. I'm going to need that picture in a minute, so I'll just draw it up here. There's an electron. It's a long way from these negative charges. Surely they can't do anything for it. It's really close to these positive charges. So surely it's experiencing the attraction from the positive charges and very little repulsion from the negative charges. But no, same game as before. We can draw ourselves a little cone, and we can integrate across this cone of force. And yeah, it's really close to these positive charges, but there aren't very many of them. And yeah, it's a very long way from these negative charges, but there are loads of them. And it's exactly the same geometry arguments that we were using before. This distance will cause the force to increase in a way that depends on the distance squared, and for this force to decrease in a way that depends on the distance squared. But the amount of charge, this is the top of the Coulomb equation, the Q over R squared, the Q bit, while the R squared on the bottom is increasing things, the Q on the top is decreasing things by exactly the same fraction, because the amount of charge also depends on the distance squared, because it's lying on a circle with a radius that depends on the distance. So it turns out that the amount of attraction from these positive charges is exactly cancelled out by the amount of repulsion from these negative charges. So in actual fact, this electron is free. This is a zero force region. There is no electric field outside of the plates. And if you think back to the last lesson, where I deliberately arranged the charges against the top and bottom of the simulating software, that's because the software is actually a bit rubbish. And if you use the software I gave you last lesson to draw a load of negatives and positives, it happily draws field in here, because it's not that clever when it's working out the force. But actually, outside the plates, the electric field is zero. So this is our electron gun. We accelerate electrons across this gap, and when they come out, they're free. So we can now work out the kinetic energy of the electrons that comes out of our electron gun, because this is just a half mv squared, and it's equal to E over V. Now, at this point, I just need to warn you a little bit about your lowercase and your uppercase letters. We've got a capital V, which I'm drawing with these kind of Roman frills on the top to try to emphasize that this is a capital V, whereas this is a lowercase v for velocity. And equally, we've got capital E for electric field strength, and then we've got capital E subscript K for the kinetic energy. So don't muddle up the kinetic energy with the electric field, and don't muddle up the velocity with the potential difference. So you can now rearrange this equation to get the speed of the electrons as they come flying out of our electron gun. And you're going to be doing a calculation on that in a minute. Okay, because this is being recorded, like I say, I'm going to skip on so that we finish and get everything done in a lesson. Usually in class, it's hard to get this in when we're all writing at the same time, but I'm going to take advantage of the fact that you can play me back on the video and make your notes afterwards. Okay, we're going to take this electron and we're going to let it fly through an evacuated space. So it doesn't hit anything, it just travels in a nice straight line because there's no forces on it, E0. And then we're going to let the electron, which is now traveling with V equal, oh no, I don't want to write that there. V equals 2eV over m. I'm going to let it travel into a region where there's a second set of plates with a new potential difference and a new distance between them. So what we really ought to do is come back to this one and put a little subscript on the V there, and on the V there, and the V there, and the V there, so that we don't get muddled up between the two different potential differences. Now this electron, when it comes flying into this region, again is going to experience an electric field. And just like this electric field, it's going to run from positive to negative, and it's going to be nicely evenly spaced because it's a uniform field again. Now, the value of this uniform field, E, will be equal to this potential difference divided by this distance. So it's a different sized electric field to this one that accelerated it because it's a different set of parallel plates. Again, when the electron enters this region, this is the force that would experience a positive charge, and the electron's negative, so it's going to experience a constant vertical force. And so as this electron travels across, there are no horizontal forces on it, so it will maintain its speed. It's not going to change its speed as it goes across horizontally, but it's going to gain speed vertically, which means that as this thing comes through, it's going to do a kind of projectile motion, but instead of gravity, which is a constant force downwards, bending it down, this is a constant force upwards, which is going to make it go up. This is your initial velocity. This is your range, and this is your vertical motion. If we were to just spin the board round, this is a year 12 projectile motion question. You've got the electric field, so if we multiply by E, you'll get the force, divide by the mass, and you'll get yourself the acceleration. So you got an initial velocity, an acceleration, a vertical distance, and a horizontal distance. This is a projectile motion question. So if I give you some of these numbers, you should be able to work out the missing one for me. So what I'm going to do, I'm going to give you the range, and I'm going to give you the vertical distance, and I'm going to give you the V1. So you'll be able to work out the velocity. So you'll have the velocity. You'll have all of the numbers. The one I'm not going to give you is V2. And what I want you to do is see if you can churn through this maths, which will make your head hurt. Churn through the maths and see if you can rearrange all these equations and revisit your year 12 projectile motion knowledge and see if you can dig out the V2 from the acceleration. So by giving you the initial speed from this, you can work out how far you go along during the time of flight. And given that you'll have the distance and you'll have the speed, you can work out the time of flight. And then from the time of flight and the vertical distance and the acceleration, you'll be able to dig out V2. So let me show you the experiment. Let me show you the equipment. Okay, so ignore the mass of wires, which are somewhat crazy. Okay, this is a high voltage power supply, goes up to 5,000 volts. And this is going to be our V1. This is our accelerating voltage. This is going to be the thing that powers the electron gun. This is the electron gun here. I'll give you a close-up of that in a second. And then here we've got another pair of parallel plates, which is the second set that's doing the accelerating. And then finally, we've got the second power supply connected to a voltmeter, and the second power supply is going to power the electric field on the second plate. So let's have a little close-up. Okay, so it's in a big glass ball so that the air can be evacuated from inside it. And what we're looking at here on this bit, these are the two plates here. So this little cylinder on the left-hand side, this little cylinder here, that's the left-hand plate. Now, I know it doesn't look very flat. In fact, it looks a little bit stretched out in a cylinder shape, but the geometry doesn't really make a difference. It's the left-hand plate. So this left-hand piece of metal here, that's the one that we're going to attach to the negative side of the 5,000 volt power supply. And then just next to it, we've got this very large cylinder. And again, that's going to play the role of the positive plate. In fact, if you look in, I don't know if the camera is going to be able to see inside, it is actually a vertical plate inside that cylinder. Can you just see that there's a vertical surface just inside that cylinder, and it's got that horizontal line across it. That's the gap in the plate. That's what the electrons are going to come flying out of. And rather than being a dot, it's going to be a fan-shaped beam that flies out, a horizontal flat beam of electrons. And the reason for that is because we need to see the electrons, and we can't see electrons. So what we need to do is shine them on a screen that phosphoresces when the electrons hit it. And the screen, we would like the electrons, some of the electrons to hit the left-hand side so that we can see, sorry, the starting side, so that we can see the first electrons to hit the screen. And then we've got some more at the back. So actually, the screen is at an angle, if you can tell that that's at an angle compared to the support. You can see that that's offset slightly at an angle, and that will mean that we get to see the electrons all the way across. If I turn on the first power pack, first thing you notice is that a light turns on, and I don't know, again, if the camera can see that. What we're actually using as our cathode is actually the filament of a light bulb. So the negative plate is actually the negative filament of a light bulb. And the reason for using the negative filament of a light bulb is because when we turn the light on, the electrons in the bulb on the filament, they have a huge amount of energy, and they are just begging to boil off the surface of the filament. They just need an excuse to do so. They just need somewhere to go, which is where the electric field comes in. So what I'm going to do is turn up the potential difference now. And as I turn up the potential difference, you see the beam of electrons start coming out. And the electrons are hitting the piece of card, and that's producing this kind of blue color, because the card is soaked in a chemical that phosphoresces when the electrons strike it. Okay, so I've got myself an electron gun, and we've got the beam of electrons flying across this evacuated chamber. So there's no real gases for the electrons to collide with. So once they come out of the gun over here, they're traveling with that speed, which is equal to the formula I just showed you on the board, which is based upon the kinetic energy, the charge on the electron multiplied by the potential difference. Okay, what I'll do now is turn on the second power supply. And I'll just crank up the potential difference on the second power supply. And you can see that as the positive plate becomes charged, an electric field develops between the negative plate on the bottom and the positive plate on the top. And so there's a downwards pointing electric field, but downwards is the direction a positive charge would move in. And these are electrons which are negatively charged, so they're being attracted upwards. They're being pushed upwards by the electric field, which is the number of newtons per coulomb, the force per unit charge, multiplied by the charge on the electron. And that will turn the newtons per coulomb into straightforward newtons. Okay, what I'm going to do is make these numbers on the screen nice. So I'm going to make that go through the number 7 just here horizontally. So what you can see is that the grid on the piece of card, that's been divided up into centimeters. So the horizontal range between where the electrons come out of the gun into this field here, the horizontal range is 7 centimeters. And the vertical change that takes place is now 1 centimeter. So 7 centimeters across is the range. 1 centimeter is the vertical change in height. And then to achieve that, what I've got down here is that the gun potential difference is on 3.7 kilovolts. 3.7 kilovolts. So your goal is to tell me, if I were to move this camera a little bit sideways so that you could actually see what the potential difference is on the secondary power supply. I could play a little game, couldn't I? I could pan across quick, and then you can like all be pressing pause on your cameras later to see if you were right. What is the potential difference on the second power supply that is causing this beam of electrons to bend by 1 centimeter vertically when the horizontal change is 7 centimeters? So I'm going to move this camera back to the whiteboard, and I'll write down some of the numbers that we've just looked at. Okay, so this horizontal range, x equals 7 centimeters. We could go better than that, couldn't we? We could do 7.0 centimeters and keep everything to 2 sig fig. So horizontal range is 7 centimeters. The vertical change in height is 1 centimeter. There's one of your numbers. There's the other number. This potential difference here, this is 3.7 kilovolts. Charge on the electron is 1.6 times 10 to the minus 19. Mass of the electron is 9.1 times 10 to the minus 31. So from these 3 numbers, you can calculate V. which is your initial horizontal speed. So that's kind of your u in your Suvat equations. So using x and v, you can work out the time of flight, the time that it takes the electron to go the 1 centimeter vertically. So x and v will give you time of flight, and then the time of flight you need to couple together with s equals ut plus a half at squared. Now u is 0, s is the 1 centimeter. So you should be able to dig the acceleration out of that. And then you can take the acceleration and you can put it into this formula where v2 is what we would like. M, again, is the mass of the electron. E, again, is the charge of the electron. The only number that I haven't given you is d2, and that's the separation of the plates vertically. d2 is 5 centimeters. Your goal, I don't think you'll have time in the 9 minutes that remains of today's lesson. Your goal is to tell me what potential difference I have set the secondary power supply to, the one that's producing this electric field. What's the value of the potential difference? Okay. By Wednesday, could you please have played this video back if you need to finish off any of your notes about where we got these things from, the derivations of E is V over D, and the derivation of the speed. Those are your notes bit. This side of the board basically is your notes bit. And then could you also have done the calculation and rock up on Wednesday's lesson, please, telling me what this potential difference is.